Hey everyone, and welcome to The Explainer. I am absolutely thrilled you're tuning in today because we're going to dive straight into one of the most fundamental, literally world-building concepts in the entire universe. We are talking about energy. But look, I don't want you to just think of energy as some boring numbers in a textbook or, those annoying lines on your utility bill. I want you to picture energy as this invisible, immortal shapeshifter that dictates absolutely everything we do. It is the ultimate master of disguise. And once you really grasp how it transforms, you're going to look at the world in a completely different way. So let's just jump right in with a question I hear all the time. Will we ever run out of energy? I mean, we constantly hear about wasting energy or conserving energy, right? Which naturally makes us kind of panic that one day the universe's gas tank is just going to run dry. But the actual answer to this question completely flips our basic assumptions about how energy consumption works. To really understand why, we need to strip things down to the absolute basics. All right, Section 1, the energy of motion. Okay, before we can even begin to understand those massive power grids that keep our cities running, we need to look at something incredibly tangible, something you can literally hold in your hand. Imagine a moving hammer applying force to drive a nail into a piece of wood. In physics, when that hammer moves and pushes the nail, it's doing what we call work. But to actually do that work, to physically displace that nail, the hammer has to possess something while it's moving. And that something is kinetic energy. Fun fact, the word kinetic actually comes from the Greek word kinema, which simply translates to motion. Any moving object has it. The math behind it is really quite elegant, and it depends entirely on just two things, the object's mass and its speed. Basically, the heavier the object and the faster it's going, the more kinetic energy it packs. And we measure this energy in units called joules. Let's ground this abstract math in a reality we can all picture. Imagine a standard 150-gram baseball being pitched toward home plate at a really fast clip, say 35 meters per second. Because of its specific mass and speed, that baseball possesses exactly 92 joules of kinetic energy. That 92 joules is the exact capacity that baseball has to do work, like, for instance, violently displacing a catcher's mitt when it smacks into it. So the really crucial point here is how work and kinetic energy interact. And this brings us to the work-energy principle. Simply put, the total mechanical work to increase an object's speed is the exact same thing as its change in kinetic energy. They are essentially two sides of the same coin. If an engine does mechanical work on a motorcycle to speed it up, well, that work directly translates into an increase in the motorcycle's kinetic energy. Moving on to Section 2, Energy's Many Disguises. Remember earlier when I called energy a shapeshifter? Well, this is exactly why. Energy isn't just about the physical movements of baseballs or hammers. It wears so many different masks. When atoms and molecules are just zooming around randomly, we feel that as thermal energy. When magnetic and electric fields oscillate, we see that as radiant energy, like light. What about the potential energy stored in your food or the gasoline in your car? That's chemical energy. It's all the exact same invisible entity, just wearing a different disguise. And we see these energy transformations happening right in front of us every single day. Look at a simple light bulb. It doesn't just create light out of thin air. It transforms electrical energy into radiant energy, plus a bit of thermal energy, which is why it gets hot. Or take an internal combustion car engine. It's taking the chemical energy stored in gasoline and transforming it into the kinetic energy of the moving car, plus some thermal energy, and of course the sound energy you hear when the engine revs up. Which brings us to Section 3, the conservation law. Okay, so if energy is constantly swapping from electrical to light or from chemical to motion, it kind of begs a massive question. What is the universal rule governing all of this? To really grasp this, let's look at a 65-kilogram diver standing perfectly still at the top of a 10-meter diving platform. Because he is totally motionless, his kinetic energy is absolutely zero. But because of gravity and how high up he is, his gravitational potential energy is fully maxed out. Now, if we crunch the numbers on that gravitational potential energy, using his mass, the pull of gravity, and that 10-meter height, we get 6.4 kilojoules. And here is why you need to remember this number. This 6.4 kilojoules is the diver's total mechanical energy. It is our unchanging, eternal magic number for the entire duration of his drop. Let's literally track this step by step across the 3 phases of his dive. In phase 1, up on the platform, all 6.4 kilojoules are stored as gravitational potential energy, or EG. But as he drops to phase 2, the halfway point, he's losing height but gaining speed.
Look at how flawlessly this baton is passed. His potential energy drops to 3.2 kilojoules, but his kinetic energy perfectly rises to 3.2 kilojoules. The total? Still statically locked at 6.4.
And this brilliantly sets up the grand finale. By the time the diver's fingers finally touch the water's surface in Phase 3, his height is 0, so his gravitational potential energy is also 0. But his speed, it's at its absolute maximum. His kinetic energy is now a full 6.4 kilojoules. The transformation is complete. The energy didn't just vanish into thin air, didn't degrade into nothingness. It just shapeshifted from pure potential to pure movement.
All right, let's bring it back to our daily lives. Section 4, powering our world.
So, the universe's energy budget is perfectly balanced. But let's pivot from the flawless realm of theoretical physics over to the somewhat messy reality of our own lives. Because honestly, if the universe never, ever loses energy, and energy literally cannot be destroyed, why in the world do our electricity bills keep going up? Why do we have those awful summer brownouts where the utility companies can't keep up with the grid demand? To ground this whole concept, let me introduce you to the Jamal family. They live in this typical mid-sized suburban home in Sudbury, Ontario, and just like most of us, they're plugged right into a massive electrical power grid. And yep, just like the rest of us, they are battling rising electricity costs. You see, the universe might not be losing energy, but the utility companies still have to spend massive amounts of money, time, and infrastructure to transform it, transport it, and actually deliver it to the Jamal's driveway. So, what's the game plan for them? Well, the Jamals started by just trying to cut back on consumption, swapping in CFL light bulbs, using programmable smart thermostats, and even looking into drain water heat recovery. But to really take control of those rising costs, they started exploring how to generate their own electricity. They looked into going off the grid, tapping into renewable resources like residential solar panels and wind turbines, basically trying to capture that free, immortal energy right in their own backyard. Because, at the end of the day, whether you are a high school physics student dropping a camera or a homeowner installing solar panels on your roof, you are participating in one grand, universal rule, the law of conservation of energy. Energy is neither created nor destroyed. No energy is ever truly lost. All of our incredible technologies, from roaring car engines to giant wind turbines, they really just exist to capture, redirect, and ride this eternal flow of energy. Which really just leaves us with one final, very personal thought to ponder. We know the rules of the universe now. We know that energy is this ultimate shapeshifter that's going to be here long after we are all gone. So, if energy outlives us all, how will you choose to harness your share today? Think about that the next time you flip a light switch. Thank you so much for joining me for this explainer.